Hello and welcome to ECMath. Today we're going to look at complex numbers in polar form and something cool called de Moivre's theorem. This theorem is all about answering the question, how can we compute a power of an imaginary number like 1 plus the square root of 3i. Now, we could do this right now by writing out 1 plus root 3i times 1 plus root 3i, etc. 9 times and distributing all of those out, and it would take us all day and we would finally get an answer. And there is an easier way, thankfully, but we need to learn a little bit more about the complex plane first. So here is the complex plane. Now you might think this looks like a regular XY plane, but it's not. The place where you have the x-axis is now called the real axis. And the vertical axis is now called the imaginary axis. Often these are abbreviated as RE and IM, so you'll see that from time to time. And these are the places where you plot a complex number. So remember that any imaginary number, z, is of the form a plus bi, where a and b are real numbers. We use z for complex numbers, by the way, as our variable. I think because the symbol for the complex number was fancy z, so little z makes sense for a general imaginary number. But remember that imaginary numbers have two parts. They have a real part and an imaginary part. When we plot these on the complex plane, we're going to plot the real part on the real axis and the imaginary part on the imaginary axis. So a plus bi is going to get plotted at the equivalent of the point a comma b. So say we had our imaginary number -2 plus 3i. Then on the real axis we would go to -2, and on the imaginary axis we'll go up 1, 2, 3. So we're going up to 3. This is still labeled 3, but we think about it as 3i since it's on the imaginary axis. And we plot the number as a dot and we label it -2 plus 3i. And that's how we plot a complex number on the complex plane. The complex plane is not a graph, like the x is not the inputs, the y is not the outputs. It's more like a number line. You just have to have a two-dimensional number line for a number that comes in two pieces. Okay, the next thing that you might have to do and that we need to do to be able to take exponents of complex numbers is find the modulus of a complex number. So here's what a problem might look like. Let z equal the same as before. Find the absolute value of z. They're using these symbols that are like the absolute value symbols. In complex number town, this is sometimes called absolute value. Sometimes it's also called the modulus. And the reason we use absolute value symbols is this represents the same thing as absolute value. It's the distance to 0. But when we say 0, we're talking about the origin. So think about it as maybe distance to 0 plus 0i on the complex plane. So let's sketch this out. We can find the modulus without any fancy formulas. The distance from -2 plus 3i to 0 plus 0i is the straight line connecting those 2 points. How do we find the length of any straight line? We make a right triangle. The height of the right triangle is 3. And it's not 3i, by the way, right? The I is dropped here. We're just using the I to tell us that that's the vertical height. And the base of the triangle is 2. So the length is got to be the square root of 3 squared plus 2 squared. So here, let's put that in. We'll show the calculation. So the modulus of this z is going to be the square root of -2 squared plus 3 squared. So in this case, root 13. And that the absolute value of that complex number we drew is just root 13. The magnitude, or magnitude is another word you'll hear for these because it's related, if you studied vectors, it's related to the magnitude of a vector. Modulus, absolute value, they're always going to be positive, and they're going to be single numbers. They might not be integers, but they're going to be single numbers, not like vectors or anything else. They're going to be single individual number. Here's the general formula. So if you have a plus bi, then the modulus of z, or the absolute value of z, is just the square root of a squared plus b squared. One thing people like to do sometimes is they get confused and they start squaring the I. You don't include the I when you're doing the modulus. You only use the actual coefficients A and B. Just like we did up here, we didn't square 3i, we just squared the 3. Here's another thing we might need to know about a complex number, which is its polar form. So if we go back and look at this number, we've noticed that it has a distance to 0, sort of like a radius. And in the complex plane, we could measure the angle of that ray we just drew and give that, a name theta. And that is called the argument of this complex number. So 13 is the modulus, and theta is the argument. And so one thing we might want to find about this complex number is the argument, the angle. And to do that, we can use some trig. So let's go to a picture and make some formulas first. So here is a picture of a generic complex number, z equals a plus bi in a complex plane with the real and imaginary axes. You can see a and b plotted here. You can see r, which is also, the modulus of z. So if you're familiar with polar, you're probably familiar with using r for that length. You can also use r in complex number terms. And then we have a right triangle. So we can then make the following formulas. We'll do cosine. Cosine theta would be a over r. So the a value is r cosine theta. And the b value here must be r sine theta. This is really familiar if you've studied polar coordinates. It's also true that r is the square root of a squared plus b squared, which is the formula for the modulus that we just gave you. But it's these two that we want to use right now. Okay, so the polar form of a complex number looks like this. If z is that a plus bi, z can also be written as r times cosine theta plus I sine theta. That's because r cosine theta was like our a, and r sine theta was like our b, and we're factoring the r out so that we only have to write it one time. So if we want to write our previous number z in polar form, one thing we have to find is its argument, its angle. So let's go and actually find that angle, and we're going to use our calculator for this. When you find the angles, they can be in radians or degrees. It is, agnostic. You just have to be sure you know what mode you're in. So today, we are in degree. I'm going to put us in degree mode, and we're going to find this angle. And we can find this angle using any kind of trig we want. We could do tangent. So tangent of theta would be 3 over 2, 3 over negative 2. We could do inverse tangent of 3 over negative 2. And we might get an angle like negative 56. Now, there's a problem with inverse tangent. We've seen this before with vectors, or we've seen this before potentially, that inverse tangent only gives answers in quadrants 1 or 4. Well, our complex number was in quadrant 2. So what we could do is add 180 to that answer. And that would give us the correct theta, going from quadrant 4 back to quadrant 2. Another option that we could do is remember that our complex number is in quadrant 2. We could think about what inverse trig is defined properly in quadrant 2. And the only function that is defined in quadrant 2 correctly is inverse cosine. So we could just use inverse cosine. And we cosine inverse of negative 2 divided by square root 13. Where is it? There we go. And we should get the same answer. So however we want to slice it, finding the angle with inverse trig, we do want to find the big angle. And that angle is 123.7 degrees. Okay, so let's go put that into our polar form. We know the radius, or the modulus, is root 13, and the angle, or the argument, is 123.7. So if we wanted to express our number a plus bi in polar form, we could write that z is the radius, root 13, times cosine 123.97. Did I say something else earlier? plus I sine 123.7. The idea is that cosine 123.7, if you evaluate all this up, you will get back to -2 plus 3i. There is an abbreviation for this I've seen sometimes, which is instead of writing this cosine plus I sine, you can write just CIS cosine I sine. And so you can write this as R CIS theta. So here you would write it as root 13 CIS cosine I sine 123.7. If you're doing just scratch work, I think that's okay. If you're presenting like a final answer or on an exam, you should probably write the full version using the cosine theta plus I sine theta. So that is the complex number in a polar form. Now, let's practice. This is your turn. So sketch out a complex plane. Please find the modulus and argument of each of these numbers, and then write each number in polar form just to see how it goes. Here are your polar points that you should have plotted. Let's go ahead and find those radii and angles. So for the first polar point, we plotted over here in green, and we went 2 over and 2 down. So here we are looking at a 45, 45, 90 triangle because we have isosceles, it's a right triangle with 2 equal legs. So this length we know is going to be 2 square root 2. We also know that this is going to be the pi over 4 equivalent. And just to show that we can do this in radians, the pi over 4 equivalent in quadrant 3 is 5 pi over 4. So we have a radius or a modulus of 2 root 2 and an argument of 5 pi over 4. And then for Z2, 4i is plotted just vertically. It has no real component, it's only imaginary. So it's plotted just 4 units up on the imaginary axis. Its angle then is 90 degrees or pi over 2. And its modulus is just 4. Distance from 0, we didn't have to use a formula for this one. We actually didn't have to use a formula or a calculator for either of these. And that's pretty cool. Let's go ahead and put these in polar form. So Z1, we would write it as 2 root 2 cosine 5 pi over 4 plus I sine 5 pi over 4. And for Z2, our second complex number, we would write it as 4 cosine pi over 2 plus I sine pi over 2. And it's sort of silly to do this, except that we're going to need it later. So you'll notice, right, that cosine pi over 2, that's just 0. Sine pi over 2 is just 1. So if we multiply the 4 in, we really do get I times 4, or 4i. So that's kind of how that translation back and forth goes. Okay, so let's talk about multiplying complex numbers. We're going to remember the polar forms, but we're going to not need them quite yet. Let's try to multiply z1 times z2, these same complex numbers, just by distributing. So here, we would do -2 minus 2i times 4i. And we would distribute. We'll distribute from the right. That's kind of fun. And so we get -8i minus 8i squared. And this is the point in our distributing where we have to do some remembering. And remember that I squared, whenever you get those, simplifies to -1. So then this becomes -1, which means this whole term becomes 8. And our final answer, let's move this, 8 minus 8i. And we could even think about where 8 minus 8i lives. Where would that live? If we just sketch a complex plane really quickly, it would live 8 units over here. Oh, too far. 8 units down there. And it'd have a radius of what? 8 root 2. So when we multiplied two complex numbers, we got a new complex number, which is always true, but we got one in a completely different quadrant than the other two. Interesting. All right, I went off camera for a second to plot all 4 of those numbers, or all 3 of those numbers, on the same complex axes, and we had to rescale a little bit, so every square now counts by 2, because something cool has happened. we took 4i and we multiplied it by -2 minus 2i, and we got 8 minus 8i. So that's the product of z1 and z2. Now look at what's happened to the angles of those numbers. We had a 90 degree, and we had or a pi over 2, and we had a pi over 4 multiple. Look at the angle of this new one. This angle is the sum of the previous two angles. The angle is, we'll just call it theta 1 plus theta 2. 90 degrees more than the green angle. And then let's look at the radius, which we previously said was 8 root 2. Well, this radius was 4, and this radius was 2 root 2. Hey, 8 root 2 is the same as 4 times 2 root 2. So, that's the key thing that happens when you multiply complex numbers. You end up adding the angles and multiplying the radii. It's a really cool property that only works because of this I squared thing causing a little bit of rotation as you multiply around. It doesn't work with regular numbers. It doesn't work with vectors. It doesn't work with polar. It only works with imaginary numbers in the complex plane. So here's the rule. Say we had two complex numbers, z1 and z2. The formula that you might look up in the book says the following. z1 times z2 is going to equal r1 times r2, so the radii or modulus for each numbers, times cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Close parenthesis. So we multiply the moduli, aka the radii. The plural of modulus is moduli. So multiply the moduli, and we add the arguments, aka the angles. So we multiply the radii, and we add the angles for any two complex numbers. No matter what they are, if we know their polar form, we can multiply them easily. Here is an example. We already kind of saw it, but let's say that we hadn't multiplied these out the long way. Then I know that z1 has a radius of 2 root 2, like we found it already, and it has an angle of 5 pi over 4. I know that z2 had a radius of 4, and it had an angle, or argument, of pi over 2. So I know z1 times z2, to follow the format, there it is, will have a radius of r1 times r2, so 4 times 2 root 2. And then we're going to do a bracket instead of parentheses just to keep it clear. Cosine of 5 pi over 4 plus pi over 2 plus I sine 5 pi over 4 plus pi over 2. Okay, and we can simplify all of that. 4 times 2 root 2 is just 8 root 2. 5 pi over 4 plus pi over 2, that's like 5 pi over 4 plus 2 pi over 4. So that's going to be 7 pi over 4. So we do 8 root 2 cosine 7 pi over 4 plus I sine 7 pi over 4. And at this point, if the problem said, oh, I'll leave it in polar form, we'd be done. But we could also translate this back into a plus bi form. And sometimes you'll see a problem that says multiply and give your answer in a plus bi. We just evaluate the trig. We evaluate cosine 7 pi over 4. That is root 2 over 2. And sine 7 pi over 4 is negative root 2 over 2. And then we can multiply this 8 root 2 in and see what we get. So 8 over 2 is 4, but then 2 times 2 is 2, so this is just going to be 8. Minus still stays, so we get 8 minus 8i, which is the exact same answer that we got when we multiplied it out the long way, and it's the same point on the complex plane. So there's two completely equivalent ways to get that product. If you want to divide two complex numbers, you just reverse this process. So if you have z1 divided by z2, You divide the radii, so you do r1 divided by r2, opposite of multiplication, and then you do times the cosine of subtraction of the angles. So theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So division, in this case, is just opposite multiplication, and it's just like subtracting. So you'll divide the radii and you'll subtract the angles. We won't do an example just for time, but we do want to do one last thing, which is take a power of a complex number. So powers are just repeated multiplication. That's it. That's all they are. So if we know that when we multiply a complex number, we multiply the radii. If we multiply a complex number many times, then we're going to multiply the radius many times. That's exponentiation. So here, let's write it down. If z is r cosine theta plus I sine theta, then z to some nth power is going to cause you to take the nth power of that radius, so r to the n, times the cosine of, and let's figure out what happens to the angle. Now say if we were to add, when we do complex multiplication, we add the angles. So if we were to do theta plus theta plus theta plus theta n times, all we would have is n theta. So that's what happens inside. We have n theta plus I sine n theta. But when we take a power of a complex number, we step it up, and the radius gets powered and the angle gets multiplied. And this is how we can take the 9th power of 1 plus root 3i. If you're feeling curious, pause the video and try it. Otherwise, we'll do it together. All right, here we go. So the first thing we need to do is write this in polar form. And to do that, I think the best thing that we can do is just sketch the dang thing out. So we'll draw a little complex plane over here. 1, and then root 3 is like up here. So the number itself is 1 plus root I. Let's make a little triangle out of this. Base of 1, a hypotenuse of root 3, 3. And from special right triangles, we know that this is 2, and we also know, so this is a special right triangle. So we know that the radius is 2. We also know that the angle is pi over 3. So 1 plus root 3i is the same as 2 cosine pi over 3 plus I sine pi over 3. I don't know why I put parentheses around that second one. Okay, so then let's follow our formula. 1 plus root 3i to the 9th should be 2 to the 9th cosine, here I'll do parentheses, of 9 times pi over 3 plus I sine 9 times pi over 3. Okay, let's do a little simplifying. 2 to the 9th, I think that's 512, but let's just check. 2 to the 9th, 512. So this must be 512. 9 times pi over 3, that's just 3 pi. So 512 cosine 3 pi plus I sine 3 pi. Hey, we can evaluate these, can't we? The cosine of 3 pi is the same as cosine pi, so this is negative 1. And the sine of 3 pi is 0, so this is just negative 1 plus 0i. And we're doing 512 times negative 1 plus 0i. So together we should get negative 512. Which is pretty weird to have an imaginary number and you take it to some really huge power and you just get a really big negative number. But it's true. I hope it's true. And to finish the video, I'll show you how to use your calculator to check. So you do need to be able to use de Moivre's theorem. That's what this is called, by the way, de Moivre's theorem. But you can always on your calculator use the I key. It's right above the period. And so you can do 1 plus square root 3 second period to get the I, raise that to a power. And it's not doing de Moivre's theorem. It's just doing like a bunch of computations. And you get the same thing. So that's how you do powers, subtraction, addition, complex numbers. Thanks for watching. We'll see you all next time.